Hello, today we're going to be going through question 5 on the Spring 2022 exam final. The questions here are listed a little bit differently than the questions that are listed in Boiler exams. So if you're viewing it from the link that was in the Boiler exam solution, I'm sure you're on the right page. But the first question that we're going to be talking about is the part A. Suppose that we are running Kruskal's algorithm to find an MST. List the edges of T in the order that they are added. So first thing I want to talk about real quick is what an MST is. A MST is a minimum weight spanning tree, which essentially means that we are trying to find the tree of edges in this graph such that we are connecting all of the vertices in the graph and we are using the lowest total weight of all the edges when you sum them together. So we're trying to find essentially the optimized tree pathway so that we can get between all of the vertices. So the way that we use Kruskal, the algorithm, is fairly straightforward. We're essentially just going to take all of the different edges in the tree and erase them from the tree and just only leave our vertices. And then we are going to slowly, one at a time, add back the edges into the tree or into the graph in the order that they are, in the order based on weight. So essentially we're going to add the lowest weight edges into the graph first, and then we're going to continue doing that, checking if we're creating any cycles along the way. And as long as we are not creating any cycles, we're going to keep doing that until we have connected all of our vertices. So the first thing that we're going to do is we're just going to essentially act like all of these edges aren't here. We essentially just have a 1, 2, 3, 4, 5, 6 vertices just kind of floating around with no edges in between them, completely unconnected. And our job is to try to connect them with the least weight edges. So the first thing we're going to do is we're going to look at all of our edges, and we're going to see which is the lowest weight of all of these edges. That obviously would be the one between C and D. And so we're just going to add this edge into our MST. Next thing we're going to do is we're going to do that again. We're going to look at what is the lowest weight edge between these. Next is going to be BC with a weight of 4. And as we're doing this, we are making sure, is the edge that we're adding in creating a cycle? In other words, is the edge that we are adding in connecting two vertices that were already connected within our MST? And so we can see that when we add in this BC, B was not already connected into the system, and so it's not creating a cycle within our MST. Another way that you can look at this is if a graph or a tree has no cycles, then there should only be one possible path from each vertice to each other vertice in that tree. And so in other words, there's only one way to get from B to D. We can go B to C to D. We'll show you an example in a second of a cycle that you can't put in because of these edges. So next we're going to look for our next smallest edge to add into our system. The next smallest edge is going to be A to B with 6. When we add that in, we check if it creates any cycles. It does not. And then we're going to continue on. Our next lowest edge is going to be 7, C to F. Once again, we are not creating any cycles with this because F wasn't part of the tree before. Next, we can add an 8. So when we add in 8, we've got two different, our next lowest edge is 8. And we've got two different options. We could either do AC or we could do EF. And the truth is that there's no reason that you should go for one versus the other. If they're both valid edges to add, you can end up with two completely valid MSTs. Let's say that we pick AC to add first. When we add AC, we need to check if it creates a cycle or not within our system. And adding AC does create a cycle because of the fact that if you add an AC, A and C were already connected in this MST. And so if you add in this AC line, then there's two possible paths to get from one vertex to another within it. Like for example, to get from A to C, you could take this path, or you could take this path. Or from A to D, you could take this path, or you could take this path. Point is that we don't want to create a cycle within our MST because it doesn't help us connect any vertices that weren't already connected. And so we're not going to add in this edge. We can continue on and instead add in the EF edge because it is of the of the next lowest weight with 8. And so when we add in this edge, we are not creating any cycles because E was not part of the graph before. So now that we've added in all of our vertices, all the vertices are connected together, we have created an MST based on Kruskal's algorithm, and that's all we have to do. We just list out the edges in the order that we did add them in. So remember, we added in CD first, and then BC, and then AB, and then CF. So I'm just gonna write those down. CD, BC, AB, CF, and lastly we added in EF. And that was the order of the edges that we added them into T. Hello, we're doing question 5B, or I think it's listed as question 7 on the Bowler Gems website, and that question is talking about Prim's algorithm. Prim's algorithm is an algorithm to find a minimum spanning tree. Earlier in this question, we did Kruskal's algorithm, which is another completely valid way to find an MST. Both of them work. Oftentimes they will find the same MST, sometimes they'll find different ones. But the point is that they both give valid MSTs. Reminder that an MST is a minimum weight spanning tree, which means that it is a way to connect all of the vertices within a graph such that you are using the lowest possible total weight of edges. So the way that we're going to do Prim's algorithm is fairly straightforward. In Prim's algorithm, we pick some kind of a starting node. It doesn't matter which one you pick. You can get different MSTs depending on which one you pick, but all of them should have the same total weight because they're all a minimum weight spanning tree. So in this case, it wants us to start with node A. So we essentially are going to start with this node. And what we're going to do is that we are going to look at the tree that we currently have, which is currently just A. And we're going to say what edges are connected to this tree but are not in the tree. We call those the fringe edges. So in this case, the fringe edges for A, for this MST right here of just A, is 6 and 8. 6 and 8 are the two fringe edges. We're going to look at those fringe edges and we're going to pick the lowest one of those fringe edges. And we're going to say, if we add in this edge, is it going to create a cycle? If it's not, go ahead and add it. If it is, find the next lowest. So of these two fringe edges that we can add in, the lowest is going to be 6. If we add in 6 into our system, we now have B in our MST as well, and we have this AB edge. And adding in that AB edge does not create a cycle, and the reason for that is that there is still only one path to get from one vertex in the MST to another vertex in the MST. I'll show you an example of when that's not true later. So next, we're going to look at our fringe edges again. So now we have the fringe edge from before that we had between A and C, but now we also have a bunch of other fringe edges. We've got the fringe edge from B to C, we've got the fringe edge from B to D, and the fringe edge from B to E. All of these are edges that are not in the MST already. We only have 6 in the MST. They are not in the MST already, but they are connected to vertices in our MST. And so we need to choose one of these to add. We are going to add in BC because it's the lowest of these. We've got 8, 4, 15, and 10, so the lowest is 4. So we're going to add in this 4 between B and C. And we're going to check, does this create any cycles? No. Adding in the BC line does not add any cycles because C was not previously connected to the MST. So it's not connected to two vertices that were already connected. Next, we're going to do that fringe check again. We're going to look at the fringe edge here between A and C, fringe edge here, 10, 15, 1, and 7. Out of those, the fringe edge of 1 between C and D is the lowest. So we're going to add that into the system. Once again, making sure that there is no cycle that's created by it. There is not. Continuing on, we have fringe edge 8, 15, 10, 10, 8, and 7. Ignore the 8. This 8 is not a fringe edge yet because we don't have either E or F in the MST. The lowest of these is 7. So we're going to add in the CF line, making sure that the line doesn't create any cycles, and it does not because F was not previously in here. Next we have the fringe edges 15, 10, 10, 8, and 8. And so 8 is the lowest edge, the lowest fringe edge weight that we have here. And so we could choose either EF or AC to look at. It doesn't totally matter which one, because MSTs are not always unique. It could be multiple of them. It could be that you could add in either of them and it would be okay. In this case, let's say that we look at AC first. In this case, if we try to add in AC, what we'll see is that we create a cycle. So if we add in AC, we would see that you can get from A to C by the line AC, or you can get it from A to B and B to C. And so there's multiple paths to be able to get between two vertices, and that means that there's a cycle within our MST. So we can't add the edge AC. In other words, adding an AC would not connect any new vertices that we haven't already connected. So it doesn't accomplish anything more. It's just adding in more weight into our MST for no added benefit. Instead, we're going to add this 8. We're going to add the edge between E and C, or sorry, E and F. And if we add that in, we don't have any cycles with this edge because E was not previously in the MST, and we now have added in all of our vertices into our MST, and so we have gotten a valid MST using Prim's algorithm. And so the question just asks us to list these edges out in the order that we added them. We added AB, and then we added BC, and then CD. I apologize, that sound was my ice maker if you can hear it. And then we added CF, and then lastly FE. One thing you will notice if you were around for part A when we were doing that is that these edges are the exact same edges that we have when we ran Kruskal's algorithm. We got the same MST in both. It's just a question of what the order of the edges that we added in were. If you're still around, I'm guessing that you're here for part C. Part 5C is on Boiler Exams website. I think it's question 8. This is one that really gave people a lot of trouble. We have been getting a lot of reports on this question. And oftentimes when we get reports on Boiler Exams, it means that there's something wrong. But in this case, it's not there's something wrong. It's just Dijkstra's algorithm is hard. And so if you're struggling with this question, don't feel bad. It's okay. Computer science is hard, especially CS251. So we'll talk about Dijkstra's algorithm a little bit. We'll talk about how it works and what some of the things are to watch out for. So one thing that I want to point out real quick is that this question's worded a little weirdly. On the exam, it was worded a little weirdly because it starts out as the title saying we would like you to find the MST for the weighted graph below, and then it has you basically do it with Kruskal's and with Prim's, and then it also says do it with Dijkstra's. But there's a key word here in this part that's essentially saying that we are using Dijkstra's to find the shortest path tree, and the reason that they say that is because Dijkstra's algorithm finds shortest path trees, Kruskal's and Prim's find MSTs, and shortest path trees and MSTs are not the same thing. That needs to be abundantly clear. MSTs are minimum weight spanning trees, and so it means that we're finding the smallest total weight among all of the edges in our tree, whereas the shortest path tree is optimized for one specific node. We are essentially trying to find what's the shortest path between A and B, what's the shortest path between A and C, what's the shortest path between A and D, A and E, and A and F. We are optimizing everything for A. We don't care about what the total weight is across the tree. So when we do Dijkstra's algorithm, there is a couple different memory types that we use, like ways that we store things throughout the algorithm. The main one that you want to keep your eye on is a array called dist. The array dist has a integer value for each vertice in the, I'm going to run out of room, for each vertice in the graph. And this dist is essentially, what you can think of it as is, it is the current best shortest distance that the algorithm knows of at that point between A and this vertice. So what I'm gonna write down the initial values that we have for this, and I'm gonna explain the initial values real quick. So for instance, the distance between A and A is always going to be 0. whenever we are starting Dijkstra's algorithm, we always set the dist value for our starting vertice, which in this case is a, to 0, and then we set all the other values to infinity. And essentially, what that means is that at the beginning of the program, the only thing that the algorithm knows for absolute sure is that the distance between the starting vertice and the starting vertice is 0. That makes sense. As far as it knows, there is an infinite distance between A and B, or there is infinite distance between A and C, or A and D, or A and E, and so that's why we have infinity for all of these values. You could also think of this array as dist to A. Usually we just call it dist, but I'll say dist to A to make that clear. So, and then we usually have another array that tells us whether or not a vertice has been visited. I'm not going to make a second array. I'm just going to make a little check mark next to each of these letters when we know that we visited it. So the way that the algorithm actually starts is that we are going to look at all of the unvisited vertices, and we are going to choose the one that has the lowest value in dist to A to visit first. The way that we usually do that is we usually do it using, you might see like a min priority queue, or I think, which is essentially a min heap. But the point is that we are trying to pick one of these unvisited vertices based on whichever one has the lowest value down here in this dist array. Obviously, at the very beginning of the program, A is going to be the first vertice that we're going to visit, because it is one of the unvisited vertices, and it is the lowest distance. Because it is 0, everything else is infinity. So we are always going to visit our starting vertice first. And so we're essentially going to put our starting vertice into the system. I'm not going to write A on it. Starting vertice into the system, and we are going to probe each of its edges. And so what that means is that we are going to look at each edge that A is connected to and say, does adding this edge into our system provide a better, faster path to one of the other vertices than we had previously thought, than we had previously guessed was the best path to that vertice? So what that means mathematically is that we are going to say, is the distance from the source node to A plus the weight of the edge less than or equal to the current best guess that we have for the destination vertice? So essentially, is 0, the distance to A, which is 0, we have that in our graph, or in our array, sorry, is 0, the distance to A, plus 6, the weight edge, the edge weight, less than infinity, the current guess that we have for B. Is 0 plus 6 less than infinity? 0 plus 6 is 6, which is less than infinity. And so that tells us that we can add in this edge AB, and it will help reduce our current distance to B. And so that makes it so that we can now say that instead of the distance to B being infinity, the distance to B is 0 plus 6, which is 6. So we are in the process of visiting A right now. One thing I want to point out is that I chose for us to visit the edge AB first. We're going to have to visit AC in a second. You can either choose to visit these edges based on the order that they are in an adjacency list, or based on the weight of this edge. I'm talking about the order that you visit edges when you are already visiting a vertice, the order that you probe edges, I should say. The order that you probe edges there is not always agreed upon in every time that I've seen this algorithm run, but generally if you're doing an exam and it has the code in the back for Dijkstra's algorithm, use whatever order that they had there. So in this case, I'm going to visit the edge AB first, or I'm going to probe the edge AB first. I don't like using the word visit because we're going to use visit for the vertices. But I'm going to probe the edge AB first, and we see that we can add in this edge into our system because it reduces the weight on B, or the distance to B. And then we're going to look at the other edge, A to C. And so we're going to say, is the distance to the source, is the distance to A of A which is 0, plus the edge weight, which is 8, less than or equal to our destination. I'm going to write down this equation that I'm saying, or this kind of question that we're asking. Is source dist plus edge weight less than destination weight, or destination dist, sorry. If the answer to this question is yes, it means we should add the edge into our system and we should change the destination distance. If the answer to this question is no, it means that we shouldn't be adding this edge into our shortest path tree. So because 0 plus 8 is less than the current value of c, which is infinity, this is a good edge to add to our system. It's going to help reduce our distance to c, and so we can reduce c to be 8. We reduce c to be whatever that source plus the edge weight was. So 0 plus 8 is 8. So now we're going to continue on. So now we have visited A completely. We can take A out of our list of vertices we still need to visit. Next, we're going to visit, we are going to visit one of the unvisited vertices, and we're going to pick from them the one that has the lowest distance value in our array. One thing that I want to point out is that I've seen people, when they do this algorithm, they don't necessarily follow that order. They say that, oh, we can just visit the vertices in whichever order we want, or we should visit them based on which edge we're probing first. No, none of that matters. What matters is what the value is in the dist array and the fact that it's an unvisited vertice. If it is an unvisited vertice and it has the lowest value in the dist array of the unvisited vertices, that's the next one you should be visiting. So because of that, we're going to look at the unvisited vertices distances, and we're going to see that 6 with B is the lowest of them. So we're going to visit 6 first. Or sorry, we're going to visit B first. And so when we're visiting B, we have 3 edges that we need to probe. We're not going to worry about probing the edge we've already visited because it's not anything new. We're going to probe B to C, we're going to probe B to D, and we're going to probe B to E. I'm going to have us do B to C first, it's the lowest. When we probe B to C, we are going to look at this edge, and we're going to say, is the source distance plus the edge weight less than the destination distance? So is the source distance of 6 plus the edge weight of 4 less than the destination distance of C, which is 8? Is 6 plus 4, which is 10, less than 8? No, it's not, which means that this edge does not need to be added to the shortest path tree. Next we go on. We're going to go on to BE. We look at, is the source distance of 6 plus the edge weight of 10, is 16 less than or less than the destination distance of E, which is currently infinity? Is 16 less than infinity? Yes, it is. And so that means that we're going to replace the current distance that we have written for E with 16, and we're going to add this edge into the system. We're going to repeat the process for BD. Is the source distance of 6 plus the edge weight of 15, so it's 21, less than the destination distance of D, which is currently infinity? Yes, 21 is less than infinity, so we're going to replace D with 21, and we're going to add this edge into the system. Next, we're going to, now we visited we've probed all the edges in B, so we have visited B. Next, we're going to choose the next vertice for us to visit. The next vertice for us to visit should be a unvisited vertice, so C, D, E, or F, and it should be the lowest distance of them. The lowest of them is C with 8, so we're going to start at C, and we're going to probe its edges. We're going to probe BC, we're going to probe CD, and we're going to probe CF. First one I'm going to probe is CD, because it was the lowest, and we're going to say, is the distance to C is 8 plus the edge weight, 8 plus 1, is 8 plus 1 less than the distance that we currently have to D of 21? Yes, it is. So because 8 plus 1, which is 9, is less than 21, we are going to add in this edge into the system, and we're going to replace D with this new low that we have, which is 8 plus 1, so 9. And when we do that, we're going to erase the previous path that we had to D, because we've now found the new best path. We're going to continue on. We're going to look at the edge BC. We're going to see is the distance to C of 8 plus the edge weight of 4 is 12 less than the destination distance of B, which is 6. 12 is not less than 6, and so we don't need to add this edge into it. We don't need to add BC into it. Next we have CF, 7, is C, the weight of, or the distance to C of 8 plus 7, which is 15, less than the current distance that we have for F, which is infinity. 15 is less than infinity, so we're going to erase our infinite value. We're going to replace it with 15. We've now probed all of the edges for C, so we can mark C as visited. Next, we're going to visit the next unvisited vertice that has the lowest distance, which is D. D has two different edges we need to probe. We need to probe BD and we need to probe ED. BD has edge weight, we should probe ED first. ED has edge weight 10, and it has a source weight, a source distance of 9. So is 9 plus 10 less than E, which is 16. 9 plus 10 is 19, which is greater than 16. And so this path, this edge, doesn't help decrease the distance to A for E. So we're not going to add this edge in. Similarly, we're going to look at BD. We're going to say, is the distance from, is the distance to D, which is 9, plus 15. So 15 plus 9 is 24. Is 24 less than the current distance that we have for B, which is 6. 24 is not less than 6, and so this path doesn't need to be added in either. So we've now probed all of the edges for D, so we visited D. Lastly, we're going to visit E. We're going to visit either E or F. If we want to visit F, we're going to visit F first because it has the lower distance of the two. When we visit F, we only have one edge that we need to look at. We need to say, is this distance, is the distance to F of 15 plus the edge weight of 8 less than the current distance that we have for E of 16? 8 plus 15 is 23. 23. And 23 is not less than the current distance that we have for E of 16, and so this edge doesn't need to be added in. So F is been visited. Lastly, we're going to visit E. E, we're going to do the same thing. I'm kind of going to skip through this because it's got the highest distance of all of them, and so adding in a new edge to vertices that we have already shown have lower distances isn't going to help. So if you try to look at this weight and look at this weight, it's not going to help decrease any of these values, and so we're going to find that this is the last vertex that we need to visit, and these are our final dist values. And so the question here asks us to list the edges in T in the order that they're added. I'm just going to show them up here. And so if you remember, we did the edge A to B first, and then we did the edge A to C, then we did the edge B to E. We also did the edge B to D in that, but B to D wasn't kept, so we're not going to list that in our list. And then we did C to D and C to F were the last two. And so that is the edges that we added into our shortest path tree. hopefully that clears up some of the confusion with the question. I believe we also have a link in this question in the written solution to this question. There should be a link to Dijkstra's algorithm visualizer that somebody made, and so that can be a nice way to quickly see how Dijkstra's algorithm explores and probes all the different edges. And so you can go ahead and you can build a tree like this in that visualizer, and hopefully that can help you visualize a little bit more in addition to this video. Good luck.